good afternoon. So I'd also like to start out by thanking the organizers for inviting me and for organizing this event. I hope the sound is good. It seems too high for me. Yeah, so we've been hearing fantastic condensed matter physics for the last day and a half. So I thought that I'd take a slightly different turn and tell you a bit about quantum optics or experiments that can be classified as quantum optics experiments in two-dimensional materials. So before I go on, I'd like to acknowledge the three key people who did the experiments, and of course, without Martin Kroner, nothing would happen in our lab. So now, if this works, it doesn't. Let's see. It seems connected, yeah.
Okay. Is it on?
It's on.
Yeah, I think you need to press it hard.
Okay. Okay. I mean, the laser pointer works, but I press the other one hard and it doesn't work. But it's okay, I can do it from here. No, it also doesn't work here, so there's a problem. Okay, now it works. Let's see, yes. So what I'd like to do is to remind you what you probably have seen in your grad courses, the AC Stark effect. You know, it's a very simple effect, but it has found enormous range of applications. And maybe, particularly in Munich, the most important one is in cold atoms. So people use AC Stark effect to make optical tweezers. This is now a competing technology for quantum computation. And also for optical lattices, this was pioneered by Ted Hensch, Emanuel Bloch, basically a few kilometers away from here. So what is the idea? So if you have a two-level system, G and E, and most atoms can be classified as such, if you tune a laser away from this resonance, then you basically make virtual excitations of the atom. Virtual excitation means that you know, you never see any fluorescence coming out at that energy. You might see some Rayleigh scattering, but if you detune, you can even suppress that. The main effect is that there will be an energy shift that is proportional to the laser intensity square. So this is the Rabi frequency divided by the detuning. Okay? So if you tune your laser to the blue side, it will be a blue shift of the transition. So the shift is always trying to compensate or to try to increase the detuning in the system. Now, this is the case with atoms, also hot atoms, and it works very well. Now, then you can ask the question, so what happens in a semiconductor? So here, we do not have simple two-level atoms. Basically, optical transitions are vertical. So we have this dispersion, and it's kind of a messy system. But you can show that if this detuning that your laser has from the band gap is large, then the same ideas work. Then you can say that all of these electrons act as independent electrons, and they shift the resonance. And you can think of it like this, that the excitation, absorption of a laser creates an electron-hole pair, but this only lives for a Heisenberg time. And if this Heisenberg time is small enough, then you will never probe whether there are 1s exciton, 2s exciton, etc. So that's why it acts like a collection of atoms, and then you get a similar AC Stark shift. Now, what happens if your detuning is small compared to the exciton binding energy? This is the relevant energy scale here. Then there is, the picture is a bit complex, because we normally describe excitons as forming a harmonic ladder. And then we also know that harmonic ladder is linear, so there shouldn't be any nonlinear effect like an AC Stark effect, right? So how do we understand shifts, or are there any? And this actually was addressed a long time ago by Stefan Schmidt-Ring. And what he showed is that actually there is an energy shift in this detuning regime, and that is given essentially by the exciton-exciton interactions times the exciton number. So the idea is that even though your excitons that you generate you have a laser that is detuned, these are virtual excitations, they nevertheless, while they stick around in Heisenberg time, they interact with each other. And this causes a blue shift. And this shift is all for copolarized excitons, there it's always with, at least it doesn't depend on the detuning. Okay, so that's the AC Stark shift, and so this is the main difference, that the detuning dependence is on the square. Okay, so now what you can then say is that one can use AC Stark shift as a way of measuring interactions between excitons, and as we will see, as I will try to show, you can also try to use these shifts as a way of understanding how different excitonic resonances, say those arise in moiré systems, are coupled to each other. Okay? So that would be the topic of my talk. So I will tell you basically how this works in the exciton case and in a simple monolayer case, and how we can determine excitonic interactions. There are some surprises there. And then time permitting, I will go on to describe to you nonlinear pump probe spectroscopy in moiré materials. And I want to emphasize that pump probe in this case doesn't create any real excitations, right? Or the pump doesn't create any real excitations. And that is important because whenever we have real excitations, then the system, the states that you are interested in might be modified. You can generate free carriers and what have you. Okay, so let's start with the system that actually Andrea, who's in the audience, built some years ago. So basically, you start out with the Ti-sapphire laser. You use part of this laser as your pump beam, so you tune the energy, and then there is a part of it is sent to a nonlinear fiber that broadens the pulse, and that is the probe that we will use to investigate how the presence of the pump as a function of their time delay modifies the spectrum, essentially to measure the interaction-induced shifts. Okay, and unless I specify, the pulses are co-circularly polarized. So this is what happens if you drive the system onto monolayer exciton resonance. And you see that it's not such a clean experiment because this is not just pump probe. This actually, you can say that it's a baby four-wave mixing. So what you see here is that there is this free induction decay signal, which is irrelevant in this case, but you cannot avoid it because it's a coherent system. So the probe is detuned. I will show this schematically. And then we compare what happens when probe is before the pump. Then we see the bare probe, the exciton resonance. And when they're overlapping, then you see the blue shift and some broadening. And broadening is due to the fact that the pulses have comparable width. So the AC Stark shift actually is different at different times. Okay, so not terribly interesting, but what is interesting, again, this is the schematic. So we change this detuning of the pump from the exciton resonance, and we look at how the line shift depends on the detuning. And you can see that there are two fits. One is not a fit, it's 1 over detuning dependence. And you see that the line shift agrees extremely well with the 1 over delta omega square. So it does look like Schmidt-Ring predicted, measures a shift that is proportional to exon-exon interactions. So this we also look at the exciton density dependence. So this is basically the pump intensity. It's very linear, and that's precisely what we expect from the linear dependence on the exciton density. Okay, and from this we can actually extract the exon-exon interaction, which is relatively weak. So we heard earlier this morning that two-dimensional materials are exciting for their strong nonlinearities. Not always, right? So if you're interested in Kerr-type nonlinearity, which is important if you want to make excitons or photons interact strongly with each other, 2D materials are not so good because this interaction is proportional to the Bohr radius, and strong confinement of the exciton reduces the interaction strength. Okay, so this is the story with neutral exciton. Now, how about when we have electrons in the system? So we all know that we now have two resonances as we inject electrons, and these we name as a repulsive polaron and attractive polaron, and this is the lower energy one, sometimes called the charged exciton, that I will focus on. Okay, so now again we change the detuning and we look at the resonance. So here you see that maybe because of the fact that the attractive polaron at these densities of 10 to the 12 is not so coherent, the free induction decay is not really visible, and we see this very nice shift that can be really large. You see that we can go up to 10 milli-electron volt energy shift by this detuned pump pulse. And again, now the detuning is measured from attractive polaron, and you see that it again has the 1 over detuning square dependence. That's good. Now, as we increase the pump, the shift is increasing. This is associated partly with, actually mostly with the increase in the oscillator strength. So the more density we have, then, sorry, I switched the topic. So the higher the electron density, the stronger the oscillator strength of this resonance is. And this, you see, it starts out weak and picks up strength. So that's good. And then if you look at the magnitude of the shift for a fixed detuning as a function of the electron density, you also see a linear dependence that at a first glance agrees with the increase in oscillator strength. But devil is in the details. If you look at this quasi-linear dependence, you see that it doesn't go to 0. It actually crosses at a finite splitting if you were to extend this linearly. Okay, so what is going on? What is going on is that the assumption that there is a density-independent interaction strength is not correct. Okay, so basically we can take into account the oscillator strength and extract how the oscillator strength, how the interaction strength changes as a function of electron density. And we see that it can be 35 times stronger interacting. The attractive polarons can be much more strongly interacting than the excitons. And this is good because then this could play an important role if you want to induce coherent interactions between excitons or polaritons. Okay, so how do we understand this? This actually is the only equation I have. So this is the wave function, approximate wave function of the attractive polaron. It's a superposition of a trion and hole and a bare exciton. Okay, so the reason why increasing density increases oscillator strength is because the quasi-particle weight increases. But at very low density, this quasi-particle weight is very small. So when you absorb a photon, you generate a trion and a hole in the Fermi sea. And the trion is tightly bound, has a Bohr radius of about 2 nanometers, but at low densities, the hole extends out. So there is a depletion of the Fermi sea that extends out to about the Fermi wavelength squared. So what that means is that the size of the exciton goes from the exciton Bohr radius now to the Fermi wavelength. And that's, in a way, how to think about the enhancement of the interactions. Okay, okay, so I should move. So I want to show you what happens when we look at moiré excitons. So this is a device that we fabricated, one of the devices that we fabricated, and Tomasz is going to talk about kinetic magnetism in this material on Friday. But I would like to first focus on what happens for the neutral exciton. So now we have not just one exciton, but 2 or 3 excitons. And what we can do is we can repeat the experiment by tuning the pump to the red side of the lowest energy exciton, which we call MX1. Now, what we can then do is with our broad probe, we can measure the energy shifts of both the MX1 as well as MX2. And we can see that this fits nicely to a detuning squared, 1 over detuning squared, where the detuning is from the MX1 exciton. So what this is telling us is that because of the low oscillator strength and large detuning, our pump mainly generates virtual MX1 excitons. And the reason why MX2 shifts is because of the interactions between MX1 and MX2, different moiré excitons. These have orthogonal wave functions, but they spatially overlap, and the interaction could couple them and result in this shift. Okay, so that's fine. So we can look at the energy shift in terms of these different contributions. What I want to bring across is that this was with the copolarized. If you look at the cross-polarized case, then we can extract some really new physics. And what we see is that for small detunings, again, there is also in cross-polarized, there's a blue shift of both MX1 and MX2. Okay? But as we increase the detuning, then instead of a simple 1 over delta omega squared dependence, we see that the sign changes. Okay? And it changes for both and at different detunings of the pumping. So what we are seeing here is so-called biexciton Feshbach resonance. And what happens is that if the probe plus the pump energy summed up allows you to reach a biexciton state, then on the two sides of this biexciton resonance, you have either attractive or repulsive interactions. And this is kind of akin to what cold atom community uses to tune the interactions from, say, attractive to repulsive. Okay? And what is really nice and new here is that while the blue one is telling us that there is a biexciton formed out of two MX1 excitons, these tightly bound excitons, this binding energy is enhanced as compared to the free biexciton by a sizable factor, 30% or so. But there is also a bound state of MX1 and MX2 excitons. So we can actually have these two different types of moiré excitons form a bound state. Okay, so that's, and we predict now that there are actually several such biexcitons, and not all of them are optically dark. And this MX1, MX2 biexciton is actually a biexciton in the continuum of two MX1 excitons. So there are some interesting details there, but we don't have any experimental evidence for it. Now, last but not least, so what happens if you look at the electron doping, so this attractive polaron resonance, how does that shift? So there it's, what we find is that the oscillator strength increases and decreases as we change the filling factor. And now the detuning dependence is better fit by 1 over the detuning. And more strikingly, if you look at the energy shift for a fixed detuning as a function of electron density is completely constant. So this is telling us something that the if I call this moiré polaron, it has a different nature than in monolayer. It's basically the system is acting as if it has completely independent trions. So each electron is independent. It can be excited, and it will respond just like a two-level atom do. Okay? So that's the meaning of this electron density independence. So basically, whatever each electron that you add shifts in the same way. Okay, so in that sense, you know, we have to be careful in keeping this polaron picture with mixtures between or superpositions of bare exciton and trion whole pair, and in some cases, the bare exciton component could be vanishing this way. All right, so I guess I'm out of time. So basically, a motivation for this kind of research, as I already indicated, comes from possibilities to explore making or rendering excitons or polaritons strongly interacting. That is, you have strong interactions at the single quantum level. Okay? So one possible candidate that we want to explore is now I learned the word, CRISPR layers. So these can actually support very small mode volume polaritons, and they're 1D. And the other one was the starting point, whether we can actually, instead of using a Gaussian beam, whether we can use a Laguerre-Gauss beam and confine the attractive polarons in order to enhance their interaction strength. And with that, I'll thank you for your attention.
Thank you very much. Paper is open for questions.
Thanks for the excellent talk, Atac. You mentioned the excitation of virtual excitons. Could you discuss briefly how I can distinguish the virtual exciton excitation from just residual absorption of the Lorentzian line?
Excellent question. So basically, whenever we tune our laser onto resonance with an exciton resonance, then what we see is that the properties, if you come in then with the probe pulse, this is modified. So somehow the resonant excitation, not somehow, it basically not only generates k equals 0 excitons, but through interactions or disorder, you generate finite momentum excitons, these linger on, and it actually is problematic if you want to extract a true exciton-exciton interaction strength. So what we see here is that because of this detuning, the short Heisenberg time of the excitons that we generate, there is not enough time to scatter off. Or you can also say that the energy detuning makes sure that there is no process that can lead to a generation of dark excitons.
And this detuning dependence that you showed is really the decay of the absorption as a function of detuning.
It's not decay of absorption, that's the decay of interaction strength. So because the density that we generate is lower, that's what that is saying. Because of the larger detuning, the population, the virtual population we generate is laser Rabi frequency square divided by the detuning square.
Perfect, okay, thank you.